Hello everybody. In this video we're going to talk about one new topic in Aspen Plus, which is fluid handling equipment. And by this we mean the handling of liquids and gases. And I'm going to go through this chapter in the textbook. Let's just remind you that this is the process analysis and simulation chemical engineering. And this chapter starts with kind of long review on the backgrounds of the fluid handling. So it starts with some general aspects about the fluid flow, what is the Reynolds number, and the simplest equation, energy equation for fluid flow, which is Bernoulli equation. And it's a kind of very famous equation that's being used in many applications. And it's based on some assumptions like what's mentioned here, that the flow is inviscid, which means that we ignore any shear stress or shear forces. The flow is continuous, that it has a constant density, and it's on the same streamline. Anyways, and then we have this modified Bernoulli equation, which includes the terms for pumps and the terms for the minor losses, which is not included in the Bernoulli equation. So this is the modified Bernoulli equation. And then it goes more through the minor losses and how we calculate them, and the major losses and how we calculate them. And this is a function of the diameter of the pipe, and the roughness and the friction factor includes both of them. And it goes through more and more details. And then the chapter goes through the piping and the equations that are, or the models that are used in Aspen Plus for modeling the piping. And this is kind of important thing, because in this part we'll see that there are many types of flows that we will face. You might have horizontal flow, you might have vertical flow, you might have liquid holdup, or and these are kind of things that cannot be modeled, or there are many cases or many systems that cannot be modeled using Bernoulli equation. Bernoulli equation is a very nice and simple equation, but this is not applicable for all the cases. For instance, if you have multi-phase flow like solid and liquid, or gas and liquid, or solid and gas, it's not possible to model this flow using Bernoulli equation, or it's not going to be accurate. You'll find some errors in calculations, and that's why you might need to look for some other equation that models your system, right? Of course, the best way to do this is to use the Navier-Stokes equation, but Navier-Stokes equation is very difficult to use, especially if the system is complex. So that's why you need to find kind of one of these models that is available in Aspen Plus, that is used for systems like the one that you are interested in. So you can read more about this. It's gonna be like short hints about each one of them, and what type of systems can be used for, or this equation or model can be used for. So again, I'm not gonna go into these details now, because they're easy to go through. And now it talks about the pumps, and this is one important thing actually that we deal with a lot, is how to use pumps and how to model the pumps. And this is how the pump work can be calculated, and this is for turbine and this is for pumps. And it talks about the NPSH and how we calculate them. Again, it's some fluid mechanics, pure fluid mechanics thing, so I'm not going to go into the calculations. Then now it talks about the compressors and the expanders, and the types of them, and the calculations of the efficiency, and all of these things. The point that's important for me now, or I want to focus on here, because we are here interested more in using Aspen Plus, not in revision of the background. And again, this chapter is very simple here in this textbook, so you can go into or read them by yourself, and you'll find the topic very easy. The point I'm interested in now is to use what kind of fluid handling modules we have in Aspen Plus. And if you check Aspen Plus, you'd find that all the fluid handling units are called pressure changers. And this is kind of a nice name to describe this category of units, because they all result in change in the pressure, either by increasing or decreasing the pressure. That's why I see that this is a very good name. And in this, we will find that we have the pumps. It's called pump or hydraulic turbine, so it works for both. You'll find here some types of pumps. It might get the flow coming horizontally or vertically. You'll find here and of course, pumps are used for mainly for liquids, sometimes for slurries, which is solids and liquids. So it's mainly used in liquid phases. The compressors are, or the turbine, it works for both as well. It models polytropic or isentropic compression. So again, it's used for gases, and it's kind of different thing, because both increase the pressure. You force the flow to go through a pump or a compressor because you need to increase its pressure, but the behavior of liquid with the increase or difference in pressure is way different from the behavior of gases when dealing with pressure. That's why or when the pressure changes a lot. Usually in gases, you would find that there is a very big change in temperature with the change in pressure, which is not the case in liquids. The temperature change is not very high. And these are the modules. All are going to be the same. I'm sorry. We find there is the M compressor, which is the multi-stage compressor or turbines, and it models multi-stage polytropic or isentropic compression. By the way, the polytropic or isentropic is how the relation between the pressure and temperature is before and after compression. So you want to find the relation between P and T before compressing and P and T after compressing, and this is how you get the relation. Either it's polytropic or isentropic. There are a lot of thermodynamic relations that relate before and after. In many cases, you find that you need to increase the pressure of a gas a lot, and this increase is going to be difficult to achieve using one compression or compressing stage, and you have to go through multi-stage compression. So you compress the flow to like half the desired pressure, and then you pass it through another compressor, either because the temperature would increase a lot and this is gonna require a very expensive material of construction, or you would require a very big compressor, and this will result in very big fixed cost for the compressor, and that's why you go through the multi-stage compressor. Again, you'd find that there is and that's why you'd see that I'm not sure if it's clear here or not, but there is kind of small cooler between the two compressors, and this is why it's like two stages, and this is a cooler in between. And that's why we might need to use this, because we need to cool the liquid or the vapor or the gases down before we go through the second compressing stage. The third is the valve, and you'll find that there are many shapes of the valve, and the valve is, as we all know, is used to uh, do some control on the flow. And this is kind of, we have a valve rating and valve design, and we know the difference. The rating is that we put the specs of the valve, and we want to see how the output will look like. And for design, I want to get this output, and I want to find what design of the valve I need. There are many shapes of the valves. There you can find this. This is kind of the shape that's usually used in the process flow diagrams. These shapes are always also used in some cases. So I believe there are going to be the same. There are many types of valves inside, and this is something we might go through in the next videos. The last two modules are the pipe and the pipeline, and this pipe is single segment pipe with constant diameter and drains and rise, and might include fittings. And what this means, and you find there are some shapes that are all the same, but what it means that uh, when you use the pipe, or the main difference between the pipe and the pipelines, is that the pipe is one segment. It has uniform. It might be like 100 kilometers. It's not related to the distance, but it's related to the dimensions. You have a constant diameter through all the length of the pipeline, and it has a constant angle. If it's inclined by angle 10 degrees, then all the pipeline is inclined by the same angle. And this is what we mean by segment. It's a same diameter, same inclination, or same rise, as it's called here, pipe. But in pipeline, you might have different segments, which is different parts that might have different diameters or different tries. So if you have a pipe that's going horizontal, then vertical, then these are two segments, even if they have the same diameter. And this is what is the difference between the pipe and pipelines. Again, you'd see that here. You might see that they look like, but they are different from inside. And this is something we will go through in the next videos, inshallah. So this is quickly an overview of the modules of the fluid handling blocks in the Aspen Plus. In the next videos, we'll go through. I think we'll go through most of them, and we'll solve some of the examples in the textbook, or we'll go through some other examples that we might find in the other textbook. So I'll see you then, inshallah. Goodbye.